Okay, thanks, Tim. I see my role as taking what has happened over the past 2 days and opening it up a bit. The last 2 days have been essentially a very practical.
Excuse me, can I do a little bit of introduction that I should have done?
No.
Mike is the senior, oh thanks, but Mike is the senior advisor for the CyberGIS project. So this is the lead in terms of what it is, what we're doing here. And so, but as well, we've been into the geodesign, because I've heard from Helen a little bit more in your background in the geodesign. So before the geodesign became a big thing here, really, is that Mike was into the geodesign thing as well, some number of years ago. But, so with those two things in mind here, it makes sense to have geodesign and CyberGIS in this talk as the lead.
So, well, with that in mind, there will be a little bit of flavor in here of the kind of position I've been adopting in relation to the CyberGIS project, which maybe I'll point out as we go through here. I'm basically interested in GIS, and so this is very much a GIS perspective on geodesign. And it asks then, how can GIS be adopted, adapted to serve the needs of geodesign? That, I suggest, is a very different perspective from Carl Steinis's perspective of the last few days, and it opens up, I think, a whole lot of interesting dimensions. So, let me begin with a view of what CyberGIS is. So, CyberGIS derives from the concept of cyber infrastructure, which is something that Dan Atkins really, I think, took the lead on a decade ago in a report to the National Science Foundation, in which he said that the future of science is about a set of activities sustained by an infrastructure, and that infrastructure will be computational, it'll be digital, and he termed this cyber infrastructure. So I see CyberGIS as essentially defined as GIS using cyber infrastructure. And that cyber infrastructure has various components. One is high performance computing. And high performance computing then means supercomputers. And at this particular point in history, that means petascale, so petabytes, or 10 to the 15th bytes, petaflops, or 10 to the 15th floating point operations per second. That sort of scale is what we currently think of as high performance computing. In 3 years, it'll be exascale. We are moving that fast, moving forward that fast. So the question then will be, what value is high performance computing to what we've seen over the last 2 days? Which I argue probably does not require petascale computing. So how do we marry petascale computing with the ideas of geodesign? And then secondly, cyber infrastructure is collaborative. And that collaboration is online. It may be synchronous, people actually talking to each other online, or it may be asynchronous, people with a delay between query and response or what have you. But those essentially are the two elements of CyberGIS. So here's Carl's model, which you've seen many times over the past couple of days, a geodesign framework, but I'd suggest not immediately linked to GIS or to CyberGIS. So that's the relationship I want to explore in the next few minutes. So to me, geodesign is a problem in two related parts. And both parts are essential, and this has certainly guided my thinking in geodesign. As Tim said, I've been involved in geodesign for some time now. I think the first meeting was in 2001, stimulated in part by Jack Dangermond, who saw geodesign as something he very much wanted to pursue. Stimulated also by a very key argument, which is that GIS had evolved over the past 4 decades into something very mundane and practical. It was being used to keep track of pipes under the street, and not to improve the world. And if you think about Jack's history, starting in landscape architecture, he, I think, sensed a certain level of disappointment that his vision had not really been realized in the way GIS had turned out. So he promoted the idea of geodesign as a distinct intervention into the world, using GIS to intervene, which is something really quite different. And that meeting in 2001 was the first of a whole series of meetings which eventually culminated in this Geodesign project. So to me, there are two very distinct parts. On the left-hand side is the stage of creating, something that's been a major part of the last couple of days, sketching and recording the sketch. And then on the other side, evaluate, analyze, predict, modify, improve, using the power of GIS to help you improve the sketch. So the creative side on the left, the humanist side, and the scientific side on the right. So aesthetics and humanism on the left-hand side, being creative, and then on the right-hand side, scientific evaluation and modeling. And to me, it's absolutely critical that both of those are supportable on top of a GIS structure. And we'll explore what that means in terms of CyberGIS. So I suspect that the vast majority of the effort in the last 2 days has been on the left-hand side. And what, to me, is also a very important part of geodesign, the right-hand side, the marrying of the rather humanist, creative design aspects with the scientific evaluative aspects on the right. That's not to say, of course, that the evaluation can't be done in a humanist way, but it can certainly be aided by a more scientific framework. So why geodesign now? I think probably the answers are fairly obvious. We're increasingly aware of the need to design sustainably. With GIS, we're increasingly able to assess the impacts of interventions. So here's the right-hand side again, using GIS to analyze our interventions, to model impacts on human health, the environment, water, etc., using models that are grounded in good science. And in GIS, we have abundant resources of geospatial data about the planet. So we are in good shape in promoting geodesign at this point in history, with access to technologies for design, evaluation, collaborative decision making. Just to go back a little bit, a lot of this way of thinking has quite old roots, and particularly in the work of Ian McHarg. And Ian unfortunately died some years ago, but some of you may have heard him at some point in the past. He was a very striking character. Not when you met him, you didn't immediately think, he's an academic. He's larger than life. And he wasn't the kind of he would typically stand in front of a class with a cigarette and a glass of scotch, which is something these days that would be absolutely unacceptable. But Ian's vision for landscape architecture was science-based. So in building a school at the University of Pennsylvania, he deliberately looked for experts in meteorology, geology, hydrology, planetology, ecology, etc., computation, and remote sensing. So this is the vision of geodesign, but it's back in the 1950s and 1960s. Ian, of course, didn't have the power, the computational power we do today, didn't have the data we have today, and so it was quite different in the way it actually worked out to how we would do it today. But you can see in that model the classic GIS idea that each science is a layer in the design, and that's very much part of Ian's vision. All of this, of course, described very well in Design of Nature, the book that came out in the 1960s. And very entertaining, if you ever get a chance, is Ian's autobiography. I forget the title at the moment, but it's a really excellent piece of writing. Okay, so a couple of examples. This is from work at Santa Barbara. I've deliberately chosen these to be very different from the kind of example you've been working on the last 3 days. This is C-Sketch. It was funded by Esri at UCSB as an application of GIS with geodesign in mind. This is the Santa Barbara Channel. Here are the Santa Barbara's about there. Here are the Channel Islands. And the problem which motivates this is the passage of container ships from Korea, China, from Asia, into the ports of Los Angeles and Long Beach. And for economic reasons, typically they come through the Santa Barbara Channel, here, and the yellow dots are sightings of whales, typically blue whales, and there's been a frequent problem of collision. Another issue in the channel is these oil rigs here. And you can see how crowded things get in the center of the channel. So the geodesign problem is to find a solution to a conflict between container ships, oil platforms, and whales. And so each of those is represented as one layer in the GIS. And we have, on the right-hand side, support for collaboration, for instant messaging. We have additional sources of data. And so this screen is the screen that one of the stakeholders in this discussion would have. And because it's a GIS underlying it, we have the ability to evaluate. So we can count, for example, the number of collisions, potential collisions between a given route and the whale population. We can estimate the distances away from the oil platforms, etc. We have all the power of GIS underneath this. And C-Sketch is now a quite nicely developed piece of software. It's being used around the world, in New Zealand, off the coast of California, and various other places, to solve problems of marine conservation, using the principles of geodesign. So you have the sketch element in saying, well, what if we look at this power? And then we have the evaluation element by marshalling all of the data that's in the underlying GIS. Yeah.
So like you can like sketch
Yep.
and can chat.
Yep.
So it's mean like when they can not have to be in the same.
Right. So it can be synchronous, distributed in space, or it can even be asynchronous. So I'm in Japan, I do some thinking during my working day, and then somebody in the US wakes up 16 hours later and continues the discussion.
So do you have a working group over there, or
Yeah.
you have to have that call and that's going?
So the software manages the working group, the stakeholders, manages the conversation. Yeah. Just as you've seen in the past couple of days with Rishi's software. So that's one example. The second example is related because it's what happens to, well, here's a schematic of the CSET's collaboration with various players in the. All right, this one's related because this is the ports of LA Long Beach. And here are the containers which arrived on those ships through the Santa Barbara Channel. And the problem here is what happens when the containers get loaded on trucks and go onto the LA freeway network. And this is 710 freeway going north on a typical day. Total congestion. These trucks are usually independently owned, and so they have, in many cases, quite poor maintenance, and so the air pollution is really problematic, especially if they're idling. And there have been studies which have suggested that the fraction of the total air pollution load in the Los Angeles basin from this is about 50%. There's a lot of idling as the trucks come back and wait at the port to pick up the next load, etc. So what can we do about this? So here's the freeway network, and these are the tracks of, we've been tracking about 300 trucks over the past few years. And they're tracks on the freeway network. What are the policy interventions? Well, we can anticipate trucks will arrive at the ports, reducing the waiting time. Or we can create virtual container yards. Instead of trucking an empty container back to the port and then trucking it out to be loaded again, we can sit it at some remote location and therefore reduce the amount of tracking. We can order the arrangement of containers in stacks so that the container that's needed is the one at the top, not the one at the bottom, et cetera, et cetera, et cetera. There are a lot of interventions. And each of these interventions can be designed and then evaluated using the GIS and its tools for transportation modeling. We had to extend some of those tools, but that's the sort of thing you have to do these days with a lot of applications. So that's two examples of the kinds of things that I see as part of geodesign, because they involve a creative design aspect, an evaluation aspect, and intervention. So let's very briefly talk about some of the requirements here and what things are missing. And this is directly a lead-in to the discussion later this morning. Right? So we need a spatial data model. Any GIS has that. It's got to have a 2D, 3D, 4D environment. It's got to recognize geospatial entities, features, all the GIS stuff. That's all there. We need the creation tools. And if you think Esri's been working a lot on these sorts of sketch tools recently, allowing a sketch to be drawn on a tablet and then captured into the database and treated as part of the database. And so, for example, if I were to sketch an area, that then becomes a polygon in the database and can be evaluated according to various criteria. So I can ask, for example, how many people live in that polygon? And the GIS can do that very easily. But is sketch sufficient? And this is something that bothers me a lot. So is a two-dimensional cartographic representation sufficient to capture a design? And I have to say no. There are a lot of aspects of the design that a simple sketch can't capture. Now we can talk about the accuracy of the sketch. Well, that doesn't matter very much. We can zoom in or whatever. But a sketch is fundamentally 2D. It can capture points, lines, and areas, but can it capture time? Can it capture dynamics? No. So how does someone sketching a design deal with things which are time dependent? Big question. More important, perhaps, is that our 2D cartographic representation cannot capture interactions and relationships. So it can't capture, for example, who lives here and works there, or what trucks need to go from this port to that destination. These are not things that you can sketch. Relationships like in what area are people concerned about some issue that's remote from that kind of relationship. And perhaps the most important is what we would call affordances, the why question, the purpose questions. Why do we need something? What purpose does it serve? These are not things typically we can capture in a simple sketch or a simple GIS database. So I think there's a very important research question here, which is how do we need to extend the basic concept of a sketch in order to capture the kinds of things that can't be expressed in a sketch? Because I think we are selling design very short if we insist that it be a sketch. There are a lot of other things about a design, and a lot of other things a designer expects to do, which are not sketch-like. All right, then we need methods, data processing, evaluation models, simulation tools. These are things that are out there. We can bring them in. So for example, models to predict traffic. So given a certain design of residential areas, working areas, the kind of models that will then predict the traffic load on each route in the network and allow us then to assess the impact. So those things all exist. They're within a GIS framework, easy to integrate as part of the evaluation process. Performance indicators. What do we want to measure in order to assess the performance of a given design. Feedback tools, so the kind of dashboard. It says, here's my sketch, and here's a dashboard evaluating that sketch against different criteria, against different standard indicators. Tools for managing scenarios, something that was working very effectively over the past couple of days, where different sketches get managed, and tools for controlling different versions, selecting different versions, extracting, synthesizing different versions, and collaboration tools, right? So let's come back then to how CyberGIS fits into this specifically. And we have GIS. We need to support collaboration, which is something that's implicitly part of CyberGIS. It's part of the infrastructure of cyber infrastructure. High performance computing, where does that fit in? Why would one need high performance computing in this kind of environment? And why would one need distributed computing? So these are questions that I've certainly spent a lot of time during the CyberGIS project thinking about. And so the most important question then, where can the CyberGIS project make the most significant contribution to enabling geodesign? So collaboration, providing a transparent, fast platform for collaboration with a large number of stakeholders. As soon as the number of stakeholders gets large, that becomes an AG problem, it becomes a CyberGIS problem. Managing a geodesign project, managing the ownership of data, managing the synchronous and asynchronous collaboration starts to become a CyberGIS project when the number of participants gets large. High performance computing, where does this fit in? Well, handling massive simulations. In the trucking problem in Los Angeles, the geography of demand for transportation is defined at the level of the transportation, what's the acronym? It's a standard term in transport. It's a piece of geography which is used for... TAZ, thank you.
Transportation Analysis.
Analysis zone, right. And LA has over 4,000 TAZs. So we're starting to see some complexity there. The interaction table between 4,000 TAZs is 16 million elements. So we're starting to see some massive need for computing. So simulation over large areas. It's one thing to simulate the trucking within Los Angeles, but get outside the LA basin and you start having even larger problems to handle, including more interactions and relationships, because these rise as n squared instead of n. Avoiding divide and conquer, because our traditional response to a problem, a geographic problem that was too big to handle, was to divide and conquer, was to hack it up into pieces, to solve the problem for Los Angeles independently of the problem for the rest of the country. We divided things up. We handled one remote sensing scene at a time instead of the whole thing. So avoiding divide and conquer is a big motivation for CyberGIS, a big motivation for high performance computing. And then faster response time. Because it's one thing to say, well, I can simulate the LA basin traffic pattern. It'll take me an hour on my dual core laptop. I'll just go and have lunch. And that's fine until you come to the point where what you're trying to simulate is actually developing in time. And your simulation, which takes an hour to run, will be an hour out of date by the time it's finished. So the need to compute faster than reality is a big part of needing faster response time. So the promise of geodesign, bridging the worlds of humanism and science. To any academic administrator, that's gold. That sounds wonderful. Oh my God, can we actually bridge the gap between our humanists and our scientists? Heavens, that would be wonderful. Implementing scientific knowledge in the decision-making context. Taking science out of the classroom and into reality. intervening in the world. Getting away from the notion that science is finished when your project is described in a journal article on a shelf in a library. Allowing the aesthetic and scientific to collaborate. Again, gold. So thank you very much.
Okay, in terms of timing, any quick questions for Mike? Clarification?
Yeah, so I like the differentiation between the sketching part and the scientific analytical part.
Yeah.
I see that's very similar, also coming from architecture, there's very much a similar distinction. Now my problem that I have is I haven't seen good tools that bridge those two. So Carl's tool is on the sketching side, that's great, right?
Yeah.
But as soon as I want to do analytics on it, I need much, much more than just the sketch.
Right.
So there's this whole infrastructure, and you described it very detailed, right? So my question would be, how can we approach that? Because I think we need that actually in the future
Yes.
to make that seamlessly integrated.
Right. So there's a lot of issues with easy integration of models into a computing environment. Right. The lack of standards. Right? So typically models are not plug and play.
Yeah.
And so I've spent a lot of time trying to think through how you might make them more pluggable. And there have been projects in ecology, for example, has had a long-standing project to try to make the set of ecological models interoperable, using standards for metadata, standards for data formats. And so, unfortunately, of course, that's just within one domain. But some progress has been made. But unfortunately, the set of models is proliferating faster than you can handle. And so, yeah, that's a huge problem.
That's the modeling side,
Right.
and I'll probably talk a little bit about that because that's what I'm focusing on. But what I'm talking about, bridging the models and the initial design, the sketch. So in architecture, we call it preliminary design. I take a brush and I draw something, and then suddenly I need to make it precise to calculate something off it. So I haven't seen, automobile industry has some things where I've seen that they go from this broad stroke, where the great idea is the important thing, to a model and back and forth. But I haven't really seen it in geodesign, and I haven't seen it in architecture, honestly.
I'm impressed by how far Esri's got, particularly with Bill Miller's group. Bill's group's been doing some really nice work on precisely that, linking the sketch to the dashboard with simple templates. In the GIS framework, once you've sketched the polygon, it becomes a precise object. And if it's in a standard format, it's going to be easy to process using any of the standard GIS tools. Which is why I fall back on the model issue, because that's more a matter of interfacing the model with the GIS framework. Once you've done that, things get a lot easier. I think the whole interaction area, though, is really problematic, because there are not, within a standard GIS framework, tools for handling the basic elements of an interaction perspective. So an OD matrix, for example, is not a recognized data type within the whole Esri suite. It is within the Transcat and some of the more calibers, more transportation-oriented GISs. But it's because of this cartographic thinking, which defines the sketch process, also defines the whole organization of the GIS. So getting beyond that, I think, is really critical. So if you think of an OD matrix as a data type, then it shows up in various places. It shows up in the return table, for example, in the modeling of the traffic network. It shows up in scattered places, but no one has really ever recognized the generality of that.
see.
and said what we need is a data type, which is a matrix, in which the one set of objects is one data set, and the other set of objects is another data set.